everybody. Thank you very much for joining us here today at 9.connects. We're going to start our deep dive webinar series and hope to go through many different things regarding the deep dives on PCB topics. Today we're obviously going to focus on vias. And before we begin and introduce our speaker, I just want to kind of give you the format for today, since it's a little different from what we normally do. So first and foremost, you probably received emails from us asking for questions. Thank you very much for responding. We got well over 50 questions. You gave us a great idea of what you wanted to know, and it also allowed us to answer a couple of questions beforehand, because we know that we only have an hour's time, and as a result of that, we probably not be able to get through all those questions during the 1 hour presentation. And of course, if there's questions thereafter that we couldn't get to, we'll be more than happy to answer those. So the Q&A sheets, and I say thus far, is that today you probably received an email from us that already has the Q&A sheet in it. So please do open it, print it out, or have it available to, for this webinar. So if you have any questions, we'd ask that you take a look at that before you ask those questions, just to see if we may have already answered them. If you did not receive that, it should be available in the handout section of your panel. So take a look there for it if you'd like to download it now. And then, of course, we'll also take any other questions that we received during the webinar today and put them together and create a final Q&A, and that'll be available upon request. So for today's particular session, please write your questions in the question panel that you have in your GoToMeeting panel, or actually GoToWebinar panel, and feel free to write those questions at any time during the webinar. So we'll be viewing those and prepping those for our speaker. And then, again, we do ask that you just take a look at that Q&A sheet to help us avoid duplicates. So maybe we've already answered something for you. Now, if there's something in the Q&A sheets that you'd like to have a better explanation of or go further into detail, please do provide the topic and the question number so we can quickly find it, because I believe it's at 11 pages at this point in time. So the ultimate agenda here is to just get into the deep dive, and I'm going to present or introduce our speaker here in just about 10 seconds. And then we'll go into the Q&A after he's done speaking for at least about a half an hour on the topic, because there's a lot to cover. And we'll go with the Q&A until there's no more questions, which is hardly likely, or until the hour is up. So with that, I'm going to turn the webinar over to our speaker, Jeff Condit, who's done webinars with us here in the past. He is a senior principal engineer with over 40 years experience in PCB design. So Jeff, take it from here.
Okay, let me see if I can change presenter here. Okay, yeah, my name is Jeff Condit, and I've been doing electronics for over 40 years as a senior engineer, and done a very, very wide range of things with high-speed design and a lot of other areas. So today we want to talk about vias. Well, why would we want to do that? Vias are everywhere, so doesn't everybody know everything there is to know about them? They're actually really fairly simple devices. The answer is there are a lot of things that you do with vias to handle special situations, and not every question about vias is one that's easy to answer. For example, what's the thermal drop of a via? What pattern gives you the most thermal conductivity per unit area? How much energy is stored in a via? What are the various methods of making blind or buried vias? What is the characteristic impedance of a via? And what must you consider about return paths? The list goes on and on. So you know, we'll just kind of jump in and start talking about these. This webinar is going to be designed to be a little bit more free-form, and much of what we present will be hand-drawn as we go, as opposed to being in a slide format. So does plugging a via, let's take a particular question. Does plugging a via change its characteristic impedance? Interesting question. Why would you want to know? Because you may plug a via or not. Well, is that going to be something that's going to affect your circuit? Well, if you think about it, if I had a sphere, a conductive sphere of copper, and I said, what's the characteristic what's the characteristic impedance of that sphere? Or better yet, what's the capacitance of that sphere to infinity or to other things in the area? I could come up maybe with some measurement of that capacitance. If instead I come along and say, what happens if I fill the inside of that sphere with some high dielectric material? Will that affect its capacitance to the outside world? Well, the answer is no, because there's no electric field inside the sphere. All of the effects that are going on with capacitance between that sphere and the other things around it are on the outside. So the answer would be no. is a via that way? Well, it partially is. If that via has a long, skinny barrel and is plated all the way down, especially if it has copper plating over the top and bottom, it's again a sealed conductor. So it wouldn't affect it at all from that standpoint. It might affect the thermal properties. It might affect its reliability, but it wouldn't affect its characteristic impedance or its capacitance to the outside world. Those are the kinds of things that are rarely talked about, but they kind of need to be known. So if I have a conductive blob and I basically charge this up, there's capacitance from that blob to the outside world. Therefore, it stores energy. Therefore, it has a capacitance because I equals 1/2 CV squared. If I pass a current through it, does it create a magnetic field? Yes, it's a conductor, and we're passing it over a link. It will create a magnetic field. So it stores inductive energy. It stores electric energy. Therefore, an arbitrary blob of a conductor has a characteristic impedance. So the question is it going to be a problem? And those are the kinds of things that need to be addressed in a more intuitive way. Since the number of shapes are infinite, then there are an infinite number of equations you could use, and you'd never know the right one. So it's best to start trying to understand it from an intuitive inside out. So let's kind of talk a little bit about in the early days of PC boards. Early PC boards were single-sided. They didn't know how to make reliable double-sided boards. Basically, they took a dielectric. Originally, they had just put eyelets in a board and soldered axial components between them. Then they found they could put laminate a layer of copper on it, and they could actually either route or they could etch that copper. However, plating through holes was a very difficult thing, and etching through holes was another difficult thing. So basically, they just made a single-sided board, and all the layout, the PCB layout, was all designed to try to be special. You place things in a way that you could connect them. Interconnection was key, but the speeds were very low, so the high-speed design characteristics were not very important. So if you couldn't make the connections, you'd put in little wire jumpers to jump over other wires to make it happen. That worked really well, but as speeds went up, they needed things that are better. They eventually learned that they could put copper on two sides, but they couldn't actually plate the vias yet. So the next step in the evolution was to say, well, let's drill out a hole of the proper size. Let's put an eyelet in that hole, and let's actually crimp the eyelet on each side and then solder it on both sides. That made some really, really wonderful connections from top to bottom, and it allowed the beginnings of two-sided design. That two-sided design worked really, really well, and the eyelets had a really great advantage in that they could carry a very large amount of current and a very large amount of heat. You could even, after you put one in, you could even put a lead into the barrel of the eyelet and solder it. So that actually took off and was very popular for a short span of time. Later, a lot of people also decided that they could put a wire through the hole and solder that on both sides. That worked well, too. That was kind of the poor man's way of doing it. But we started noticing in the industry that things were getting trapped in the hole, fluxes and resins and uncleanliness. And so corrosion was starting to occur in other things, and the process needed to be cleaned up. So eventually they found ways to actually plate through holes. And in the early days, you couldn't plate very far because the plating at the outside of the hole was much fatter than on the inside. So the boards had to be relatively thin, or the holes had to be very large in diameter. Gradually, that process has changed and got better and better and better. But with that, the speeds going up, it's now gotten to the place that the vias are so short, that the frequencies are so high, the wavelengths are so short, that vias are now really coming into play from a high-speed standpoint. We have to make them very clean and impedance controlled. So so that's kind of where we are today. Let's look a little bit. Okay, let's start talking about some of the effects of a barrel. New screen. Okay, let's say we have a printed circuit board. Here's a printed circuit board. And let's assume that we have let's say that we have copper on one side and on another side. And we decide to drill a hole through the board to connect the two, and then we plate it so that there is now copper on the insides of the holes. So we end up with a land on the top, a land on the bottom, and a plated through hole. As you can say, we probably could come along and say, let's pass a current through this, and that current will flow, and it will go down through the barrel, and it will come out the other side. So we know what the current is, but what is the drop across this? We pretty well know how to calculate the resistance of a trace. Because we know that we can take its width and its thickness and calculate its cross-sectional area and then multiply by the length and the resistivity of copper. But what about vias? Well, for DC currents, it turns out to be very, very similar. We need to know the cross-sectional area of the via. We need to know the cross-sectional area via. The cross-sectional of the area of the via looks pretty much like this. Area of the outside diameter minus the area of the inside diameter. If you want to talk about radiuses, which is what we normally do, let's assume that we have a via. It's pi r squared for the outside minus the inside, right? Or if you wanted to put it in terms of diameters, okay, so we can calculate that area. It's not very hard. What else do we need to know? We need to know the resistivity of copper. Typically, you can look up the resistivity of annealed copper, and you will find out that if you're talking about in units of mils, it would be something like 606 times 10 to the minus 4th ohm mils. Of course, it goes up, and that's at 20 C. This number is going to go up and down. Clearing that up. That number is going to go up and down depending on what units you're in. For example, if you tend to work in millimeters, it would be rho annealed in millimeters. This is in mils, is equal to 1.678 times 10 to the minus 5 ohms millimeters. So you can go ahead and you can calculate that. That area, but you also have to take into account the height. The height of the hole is again the other factor. So the longer the hole, the higher the resistance. Hence you come up with some very basic formulas like the resistance is equal to the resistivity times the height. It goes up with the height, and it goes down with the area of the cross section. Which, again, if you were to just plug that back into the same formula, would be pi over 4 outside diameter minus inside diameter. Now these equations we can put in the notes, so you don't need to necessarily be taking these things down. But it would be interesting to see what that does. For example, let's assume that you had a hole that was 8 mils drilled diameter, and let's assume it was 62 mils thick. Well, in that case, your resistance would be equal to, just plug it into the formula, outside diameter, inside diameter squared. So we were able to handle things fairly easy, like the resistance of a via. That's just one part. Things get a little bit more tricky if you start talking about high speeds, though, because skin effect now has a problem in that as you go up in frequency, if you have a conductive sheet of metal, and now you have a field, electric field, and the field tries to penetrate through there, through the conductive material, you end up causing currents to flow in the surface which oppose that. So effectively, if you are less than the skin depth, there is some depth that will penetrate. If the material is thicker than that, well, the electric fields will not penetrate all the way through because they can't. They're opposed too much. It also turns out that if you're trying to conduct those high frequencies down a conductor like a wire, that same effect is going to push all the currents to the outside such that there will be none flowing in the center. Hence, your resistivity becomes only that, effectively, of a tube. So the resistance goes up from what it would be at DC. That's called the skin effect. So how can we calculate that? Well, in order to do that, you need to find out what that skin depth would be. Equation for skin depth, just for reference. Okay, where we basically have the resistivity, and we actually have the frequency coming in again, and we have that's the frequency in radians. Key thing to see is that instead of just having a normal type of equation, we now have these other factors that fall off and create that an ability to squish it down to where we only have a narrow ring of conduction. Now this will happen in vias when you're carrying very, very high speed signals. Note that at terabit type signal rates, the actual skin depth may be less than the surface roughness of the barrel of the hole. And as a result, it may be that the signal cannot flow in an area where there's unimpeded copper. It's like being in a bunch of hills and valleys, and it has to stay only within a few inches of micro inches of that. And as a result, at terabit frequencies, the barrel may be very, very lossy and have a high impedance. So skin effect can be important. At DC, it doesn't matter. At 60 hertz, the wavelengths are so long that it can't possibly affect you for any reasonable sized via. The larger, the higher the frequency, the bigger the problem is. So what is a high frequency? Well, you can actually go through the equations, or you can start to use some general rules of thumb to get you close, which is usually the best place so that you don't spend time calculating every possible equation. Again, what ends up happening is that the first thing we always want to look at is what is a quarter wavelength. Okay, this is kind of a generic rule. If a quarter wavelength if your material is very, very thick with regards to a quarter wavelength, then you're going to start having some effect. If your material is very, very thin with respect to a quarter wavelength, then you're not going to be having much effect because the speeds and frequencies aren't going to be able to push things around because it isn't in one state long enough to do that. So the second thing is you can go into this equation and you can see that we have a term that is recurring. We can look at that term, And you can plug in the resistivity, you can plug in the frequency, and you can plug in the dielectric constant, and you can actually see when that becomes significant in comparison to approximately 1. If this is very small, if this part, let me grab a different color, if this part is very small and this part is very small, you end up with 1 and square root of 1, square root of 1, and everything comes out the way you would expect if the latter portion is equal to 1. So you can see what you're trying to look at. That can give you a hint. In general, most vias that we're talking about for, for gigabit type signals, they have some characteristic impedance and some other effects, but the skin depth is not getting to a place where it's really highly significant. When you get to terabit signals, it's very important. So that'll give you a rough feel. Again, you can do the calculations. Okay. Let's look a little further. Okay, traces and vias as transmission lines. Consider an infinitely long wire in space. Here's an infinitely long wire in space. Okay, because you can put added charge into each segment and change its electric field, because I can put charge onto this. I can take some Q and I can put it onto here. I can change its voltage. I can generate an electric field off into space. That electric field stores energy. Hence, this thing has the ability to exhibit the equivalent of capacitance per unit length. Also, if I have the ability to squirt a current through this comes with a voltage. If I can squirt a current through this, I can create a magnetic field in here. That magnetic field can store energy. Hence, I can actually have inductance, which is to infinity. I don't have to have it in the wire. I can talk about this kind of, I should try it. Capacitance typically will be to infinity, although you can talk about it being back and forth on the same wire. The inductance is typically per unit length in the wire. Both store energy, both exist. Hence, there is a characteristic impedance that this wire has. And that's important to know because that's what you have to match if you want to send energy down this wire. It's important to know that these electric and magnetic fields are coupled. If the voltages stored in the capacitance are left at a period of time, they will cause current to ramp up through the inductor. Hence, there is a propagation speed, okay, which is less than the speed of light by a factor of the dielectric constant. So we have a classic transmission line with all of these things active. Well, in a very simplistic way, if I had a flat bar, it might have slightly different effects, but in the long run, it's going to have inductance, and it's going to have capacitance, and it's going to have the same kind of effect. If I have a wire that's that way, like up above, but I hollow it out in the middle to where I have a tube, it still has the capacitance. It still has the inductance. Hence, it still has the a characteristic impedance. And further, if I take that to a place that I just take a short segment of the tube and put it in a PC board, I have, guess what? A short segment of a transmission line. And so vias actually act like transmission lines. Okay. Note that when you're thinking about vias, you need to understand that there is a magnetic field. Generally, if current is flowing through a via, there is a magnetic field being generated by it. There is also an electric field being generated through capacitance by it. So when you're using vias, you certainly do not want to put a very sensitive via right next to it where these capacitances will couple. The further away, the better. You have to go a distance away to make that happen. Likewise, if you have a via very close by and you make current flow through one, and if the field couples from another, one via into the next via, you will basically induce current in the second via. So understanding this gives you an idea of, well, I need to be far enough away and shielded enough that I'm not going to be creating an electromagnetic problem. Now, these are very intuitive effects. If you tried to run mathematics for them in all cases, you would find yourself writing books and books on it, and it would take a very long time. So in general, what you want to do is find some feeling for how far away should they be. Well, if you want things to be coupled, maybe it's okay that they're close. If I have a differential trace, and it goes through a via here, and I have the other side, if I have a trace, it's part of a differential pair, and I have another one there, and these go down and at the same place, and all the spacing of this is approximately equal, some fraction of a wavelength, then because they're supposed to be somewhat coupled, that's going to be okay. But if they're different signals, then you probably want to take one of them and move it much further away. How far away? Well, it depends on a whole bunch of other shielding factors, but it's generally large in comparison to a quarter wavelength is ideal. Otherwise, you have to make it, if you take a trace and then you put a ground plane directly under it, then elsewhere on the ground plane, it can actually be closer because this first trace will be interacting with the ground plane so intensely that very little will be left to get out and actually couple to the second trace. So proximity of things like ground planes make a big difference. All right. Okay, let's talk about vias in solder mask. So you have a via, and in this via is a hole, and it goes down to another mask, to another pad, land. We have a land, a pad, and we have a via, and we have a barrel, and the barrel has a particular thickness. Now, we will oftentimes not want to have this in the soldering operation, since this is part of a board. We may not want to put this in say, a wave solder bath because the solder would go down inside the hole, and that would suck up a bunch of solder. That may be okay, that may be not okay. If we have a pad over here and it's connected by copper, and we put solder paste on it, what we don't want to do is heat it up and have most of the solder paste end up going down the hole. So we typically put the solder mask coating on the outside of this. So basically, outside the hole, we need to leave the pad uncovered. We may want to leave the via uncovered, but it's necessary to put solder mask outside of it. All right, that's great. So the first question comes, how far away from this should it be? How far should the solder mask be from the hole? Well, it depends. Do you really need to leave all of the pad uncovered? Not necessarily. Sometimes people decide that they want to tent part of it but leave the hole open. Generally, most time people say, I want to leave that completely uncovered. My guess is why they do that is because when you have a pad, you definitely want to leave a surface mount pad. You want to leave the entirety of the pad open. Now, it turns out when you make this, you have a size of an artwork, and you say what the width of it is, and you say what the length of it is. But when they make it in reality, it's actually going to have a little bit of tolerance. Okay. When you make the width, it will actually become the width with a little bit of tolerance. You can try to figure it out, but it's going to vary. So what do? You normally say, and the solder mask itself will be at a place where its registration, it will have a hole that's slightly different than the size that you said, and it also may be misregistered slightly based on manufacturing tolerances. So you want to make sure that this opening in the solder mask is far enough out that even with all of those things going on, that you're not going to get a problem. So if the solder mask opening were to shift with respect to the hole, as long as it is open, you will not have any problem putting the lead of a pad onto it and soldering it. So in general, you need to look at the manufacturing tolerances for both the lead and the solder mask and the registration of them, and add an allowance on the outside to the size of the solder mask. The same thing you can do on a via, but if the via is not part of a pad, if it's just a via for connecting between layers, you can leave it open. You could even tent it. Tenting is where you close it all together, and it would be okay. However, there are some things to know about vias and solder mask. Sometimes people want to insulate. Well, solder mask is not a reliable insulator. In other words, you can't guarantee that it will actually support a high voltage. If I have a PCB and I have a via going through the board, and I want to mount this down to say a metal cooling plate, and I have a small amount of solder mask on it, I could say, well, what would this solder mask ideally, how much voltage would it normally support? Well, the trouble is it may not support any. First, when you put it down, it's so thin that it can be mechanically damaged and actually short out. Second, it can have pits and voids in it, so that if there was, say, a little bump or a little something, it's actually air, it's not the material. Second, third, if you have a via, if you're using a liquid photoimageable type solder mask, then it turns out that it may actually pop in the middle of a hole. That may actually break to where the solder mask covers the land of the via, but there's still a hole there. It's not reliable because it's a liquid, and any little changes in pressure and other things can cause damage to the hole. That's why when you're using an LPI type solder mask, you don't want to tent a via. If you tent only one side of a via and leave the other side open, well, then stuff can get up in the long barrel of the hole. If you have a barrel that's say 8 to 1, 1 in width and 8 in length, it's very, very hard to clean that barrel unless you can wash cleaning solution all the way through it. So if the solder mask comes along and breaks on one side and something gets into the hole, you'll never be able to clean it out unless it's open on both sides. You could say, well, then tent it on both sides. Well, that sort of works. With LPI, you stand a chance of breaking it on one side and not the other. Otherwise, if you're going to try to do that, it's best to use a dry film because it's much more reliable. And a dry film type solder mask, being oftentimes thicker but definitely more robust, won't pop, and it'll seal the top and the bottom much more reliably. So you can tent top and bottom and then clean it. Even if you're using a dry solder film, you do not want to only tent one side and not the other, because no matter which one you do, you're going to end up having an open hole that you can't wash through. So either leave them all open, which is fine for most vias, or if you have to tent both sides and use a dry film. Okay. Again, some of these things, especially the ones used for controlled impedances, have larger thicknesses. When you have a printed circuit board, let's talk about a printed circuit board. If you have a printed circuit board and you're trying to make a controlled impedance trace on it, well, okay. the impedance, you may have a ground plane in it. Let's say this is the top layer. You have a solder mask over the top. Then you have another layer of dielectric. Then you have another traced layer. And so let's say that this is a plane. And let's say this is where your traces are. Well, much of the electric field will go between the top trace and the plane. Many of the field lines, if you look at them from this trace, will basically go down. But some of them go up. To the extent that you have signal lines coming off of this trace that go up and out before coming down to the reference plane that are going through the layer of solder mask, the dielectric constant of that solder mask can be substantial. And so whether you have it and whether or not it's thick or not will affect the characteristic impedance of the traces. It also will control how many of those field lines are up high versus actually being bent down low. So the more dielectric on top, the less amount of magnetic and electric field actually project up above the board. So you can't just say that the solder mask has no effect to characteristic impedance. It does on the outside of the board. However, if later on down inside the board between another set of planes, you do have, again, another signal trace, the field lines from this trace will pretty much be contained between those two planes. So the solder mask doesn't affect those. Just be apprised that if you're using solder mask on the top surface, you're going to have to take that into account in your characteristic impedances. So when you make vias, you make a via, your decision on whether or not to tent it has to include various things like, is this on the surface? Is this a high-speed signal? If so, whether or not you tent it with solder mask will make a difference. Okay. There are a few rare things that are done with solder mask that I've seen. Sometimes people will say, I want to put solder mask on the outside because this board has to be sealed in some kind of a place, and I need to make sure that, say, no light can come through this board because there's light on one side and not on the other, especially if it's like some kind of photographic or imaging type board, in which case they might use black solder mask just to basically block light from making it through the board and also through the holes and vias. There's other such things that sometimes are done. Sometimes people will actually have a place where there's a pressure on the bottom and there's a pressure on the top, and for some reason they need to be sealed. There's a different gas on the bottom than on the top, and they're trying to measure some pressure or do something. So sometimes they will actually use solder mask to seal those things. It can't take very much pressure, and it's not designed to do that, so I certainly can't recommend it, but I have seen it done. So again, watch for the specialized purposes, and if any of them come up, you're going to need to make sure that the solder mask you choose can handle that. When you make a board and you put solder mask on the outside, it will add a very slight thickness to the outside. An LPI solder mask might be on the order of 1/2 to 1 mil on a layer. Some of them, if you're doing something that's a controlled impedance, this could be several mils. So when you go to decide your overall board thickness, you need to take that into consideration. Okay. So let's talk about BGA patterns. Let's say we have a BGA, and this BGA has a bunch of pads. There we go. Okay, so we have pads on a BGA. How are we going to connect to internal layers? There's two general philosophies that are used regularly. One is to put the vias offset from the pads. And then connect them with traces. This is the most common way that's used. That way, a surface mount pad doesn't have to worry. It can be surrounded completely with solder mask, and the surface mount pad won't lose any of the solder allocated to its ball. That works really, really well. But you have to make sure that the solder mask is adequate to prevent the solder from wicking from the ball into the via of the hole of the via. So this is oftentimes a very, very tight space. If you get down to something like 0.5 millimeter type pitch, this becomes essentially impossible with, some people do it, but to get to handle all the tolerances and everything with typical manufacturing techniques, it's very, very difficult. So instead, when you get down to a very fine pitch, many people say, well, we're going to have to resort to, again, putting the via right smack dab in the middle of the pad. So you have a surface mount pad, you have a via. The problem with this is that the via, so if I have a pad, and then I have the via actually inside the pad with its hole, you're going to end up with a hole drilled all the way through the pad. Well, that's going to suck the solder away, so you have no way to deal with it with solder mask because you can't put solder mask over the pad. Hence, it's necessary to plug the via. Plugging of vias is has done a lot on these very small things. It is an expensive process. Usually, these via the diameter of these holes gets fairly low. It can be a few mils. It can be like 5 mils in some cases, which is pretty small. And so how do you plug that? Well, on the surface of a board, they might oftentimes come along and say, okay, here's the via that you need. First, in order for this to be 5 mils, if this is 62, it's going to have a very long L/D ratio, which makes it, number one, hard to manufacture. Maybe it'd be manufactured with micro vias. You'd say that'd be great. But micro vias are hard to plug. Why is that? Well, let me stop a little bit and say, if you're plugging with a material that's conductive, then it's hard, because typically what they'll do is grind up something like they'll powder aluminum or usually silver, and they'll take the silver and they'll put the silver inside a binder of epoxy or whatever material they're using, and then they'll try to pump this down the hole. How do they pump it down the hole? Well, they typically put pressure up here and a vacuum down there. Oftentimes they'll use a squeegee, a rotating squeegee on the board to actually rotate over and try to push it down the hole. Well, if you've ever tried to put large rocks into a pipe, you'll find that they jam up. That's exactly what's going on here, especially if the surface texture of the via barrel isn't perfect. So filling it with silver is great because it indeed increases the thermal conductivity, which is usually the problem, and increases the electrical conductivity, which is sometimes a problem. So plugging with a conductive material is great if you can do it, but in this particular case, it's very, very difficult. So oftentimes they'll just plug it with an epoxy after they plate it. If the length to diameter ratio is greater than about 12 now, you probably are going to have a special process done. It used to be 8 to 1 was a normal process, and most houses could do that. In the very early days, 5 to 1 was more typical, but 8 to 1's been around for a long time. 12 to 1's showing up at most fairly normal houses. There are houses out there that can do 25 to 1 or even 40 to 1 through very, very specialized plating on, plating off type processes, but this is big dollars. So you want to stay away from that unless you don't mind. If cost is no object on your board, then you can consider long holes. But remember, they're still fragile, and they act like a small wire, and so they may not electrically meet your needs. So if you're going to do via and pad, you're going to still have your solder mask around the outside of these. You're going to have the holes drilled. Once the hole is drilled, it will typically have to be plugged, refinished, plated over with copper, so that when you look at it, you see nothing but just a flat pad, knowing that underneath there is a hole that's plated all the way through. And you can do that, and it works, and it's kind of a pricey process, but a lot of people are using it. My best statement is if you can use something that's not that fine of pitch, you'll save yourself a lot of cost and a lot of risk on a board. Sometimes the absolute size of the board is the driving factor of everything. Oftentimes it's been arbitrarily chosen. So if it's been arbitrarily chosen, you don't need to do that. We're going to have to wrap it up here. I know I've been going on for a while. We do have several questions. Okay, how do we determine optimum size for high current application connecting internal and external layers? Okay. So if you have a PCB, and on this PCB you have a trace, and this trace has a lot of current going to some kind of interconnection, and now you want to connect this external layer to some internal layer. I'll draw, here's an internal layer. And so what we want is to actually have some internal trace. So somehow these need to be interconnected, okay? What is the optimum size? Well, here's the difficulty. In order to do this, you need to kind of know what you mean by optimum. As you push current down here, that current is going to be seeing some kind of resistance per unit length in the trace. Once it gets to the barrel of the hole is going to have a different possible resistivity, but the same current has to flow down there and then out on the other trace. Okay, one approach that is a first order approximation is to say, if you look at this trace, okay, it has a certain thickness and it has a certain width. It has a width and it has a height, and width times height equals area. And that's on the outer surface. If you look at the other trace, you'll see that it also has a thickness and it has a width, and therefore width times height is the area on the inner layer. Ideally, if there were no special heat problems, you'd say, great, if I have the same amount of cross-sectional copper on the top as on the inside, then it would have the same drop per unit length. That's great. But the outside can dissipate heat way better than the inside. So if you are thermally limited, you can get by with less copper on the outside, okay? But when you get to the inside, you need more copper. Well, you could say, let's make the barrel, okay? Sorry. Let's look at the barrel. If I look at the barrel, I'm going to see that it is cross-sectional. It has an OD and it has an ID. And I can take the area of the OD minus the area of the ID of those is equal to the cross-sectional area of the via. I can make that roughly equal to what it is on the top and the bottom if they're the same. If it's just carrying current, fine. But if you're trying to dissipate heat, now you need to look at the various things. As a general rule, if I were to say this is adequate on the outside, this is adequate on the inside, but this is the larger of the two because it's on the inside and cannot generate heat, I would say you need to make the cross-sectional area of the via roughly equal to the size of the trace on the inside, because that's the worst of the two. There will be some heat able to get away from the via. It can conduct up to the surface and onto that trace. And it can conduct down and onto the other internal trace. But its ability to dissipate is somewhat limited. If your board is very, very thick, it may even be worse than that because the via doesn't have much surface area to dissipate heat. Okay, if you have a board that has a plane layer, that's an entirely different thing because you may be using the plane layer to dissipate heat. Overall, you're going to have to decide, how does the heat get off the board? Just pushing it on from one layer to another doesn't get it off the board. Does it have to just kind of come up off the top surface, or does it have to actually conduct to a plane layer that has a mounting hole, and the mounting hole is bolted to some kind of a chassis? You need to decide your thermal paths. So you can't actually get an absolute answer to that unless you know exactly where the heat is going. Okay, another question. Does moisture get trapped if tent both sides? The answer is yes and no, depending on how you do it. If I have a via that goes from one side to the other, and if you come along and tent it, let's say I tent it over this side with something, and I'm going to come along and tent it over the other side. The hole is now as if it's like dry film. Then it'll pretty well seal that hole. It's very robust. People use it to seal the hole on both sides fairly often. If the hole is sealed, then there is air trapped in it. If this was sealed and made at the time that the board was ultra clean in a fabrication process, the inside of that barrel may be sealed, but it can be very clean. And many, many people rely on that. Some people don't want to rely on that, so they want to clean it. All right, but if you have it tented both sides with dry film, then oftentimes you won't get moisture trapped inside because the dry film blocks it from getting in. All right? So this is oftentimes done. Otherwise, how do you keep it out? Well, there's only a couple of ways. One is to completely plug the hole of the via at an appropriate time. Before you actually put any masks on, you jam all that epoxy down in it and make sure it's completely plugged and sanded off flush. And then when you go over and tent it, there'll be no actual volume that the moisture could get in. So that's a really good thing to do, but it's a pricey and difficult and time-consuming thing to do. So most people don't do that. Again, do not use LPI if you're going to be doing the tenting over the via holes, because what happens if 99% of the time it's tented? That means 1% of the time the top could be open, okay? And 1% of the time the bottom could be open, which means about 2% of the time it could be open on one end only. Hence it will get, if you get any crud inside, which is typical from soldering and post assembly cleaning operations, you'll get it in the hole. You'll end up with moisture. It will be a problem. You don't want to do that. Hence, tenting both sides is the most common way to do that. Plugging is a possibility. Again, do not use it on one side. Even if it's dry film, do not tent one side and not the other. Hopefully that addresses the question. For high-speed differential vias, solder mask is preferred to cover both sides or don't really care much. Any study or knowledge? Yes, for high-speed differential traces. first of all, I guess this doesn't, okay, differential vias, okay. When you have differential traces, they're on the surface of the board, we'll just leave that as it is. When you have differential vias, you're attempting to send both signals through the board at the same time. And the question here is asking about should you cover both sides or not, or don't really care. The answer is yes, you do care, okay. And it isn't that you don't care, you do care. So if you have one trace going to one kind of a pad, and the other differential trace going to another kind of pad, and I'm going to ignore for a minute what the spacing of these and the ground return paths are, and I'm going to draw it kind of more schematically than physically, and these go down to some other layer. This is kind of vertical. So this, I'm just kind of trying to schematic diagram this out. If this is, again, if this is the diff pair, and the other side is also a is the continuation of the diff pair, and you have some kind of vias going between them, you need to make sure those barrels stay clean, okay? You can, again, choice number one, get a different pen. Choice number one is to tent two sides with dry film. Option number two is plug. Option number three is leave open and clean. As long as both sides are completely open, your cleaning process, if it's good, ought to be able to do that, as long as L over D is on the order of, 8 to 1, sort of. If it was 10 to 1, it probably work. If you try to get 25 to 1, I wouldn't trust that as a cleaning process. So those are basically your options. Are there other options? Possibly, but they get kind of strange. So I think that just, again, no LPI in this case. Doesn't mean LPI can't be used. It just needs to have the holes remaining open. Okay. One more question. If there is an existing batch of boards that have paste wicking issues, is there any way to add solder mask after the fact? Oh boy. Yeah. Okay. So let's assume that you have a board, okay, and let me draw that a little better. Let's assume that you have a board here. And let's assume that you have a trace or a pad which has a trace on it to something, okay? And the solder mask now kind of goes around like this, okay? So there's an opening in the solder mask where an open via exists, and the solder itself is going, solder from here is wicking and going down the hole. What can you do? Well, after the fact, number one, it's best to make sure that the distance between those two is sufficient that you can run the solder mask between them. That's number one, but that's after the fact. The horse is out of the barn. So what can you do here? Well, the only thing, there's two things you can do. Number one, you could, after the fact, after this is made, you can come back and conceivably conformal coat, i.e. put a little drop of epoxy or some other conformal coating mechanism over this hole before it's soldered. But again, this would be after it's fabricated. If after the fact means after the board is completely assembled, then you have another problem. If the board has already been assembled, then the solder that was under this has already gone down the hole. Therefore, this joint is starved. Therefore, you can't fix that outside of reworking it. Therefore, you have to take the component off, clean it up. You have to then put the conformal coating of some kind or epoxy blob over the hole and path, put the new part back on, and then resolder. So this gets to be fairly difficult. Again, think about it when you design that. Make sure there is no path that the solder paste can get off the pad. And one way to do that is to look at the actual outputs. I kind of prefer to do it in Gerbers, but if you look at it, line it up, you can say, here's the solder mask outlines, here's the pad outlines, and you can look at them and say, is everyone completely surrounded or not? Also, if you set it up carefully, most design tools, PCB design tools, can have some mechanisms for warning you for that, but not all do. So again, depending on which tool you're using, you need to be cognizant of it. You need to make sure that there's no through-hole type path. And it doesn't matter whether this through-hole is a pad or a via. If its hole is open, you're going to have a problem. If it's a pad that's not soldered, if you have a dip component with going into a hole, and you're doing a wave soldering, well, the wave soldering will have probably been done and filled that up, hopefully first. If it wasn't first, then no, it won't. But the other surface mount pad, if the other pad has been completely soldered, then theoretically there wouldn't be much wicking as long as this trace is short, because that pad is already full of solder, and the solder would have come up and flowed partway down that pad. Of course, if that pad is very long and it's already soldered, then it could be the trace itself will take enough solder off of the pad that you would have a problem. So, all right. Thank you very much.